So in this lab, what we're going to be doing is we're going to first look at three different transition metals, copper, iron, and zinc, and figure out what would be the optimal wavelength to take their measurements, looking just at the visible range, so between 400 to 800 nanometers. And the reason why we're looking at those three metals in particular is because what we're then going to try to do is figure out the percent of copper in a sample of brass. Now, brass is an alloy of copper and zinc. So I need to know the wavelengths that copper and zinc absorb at so that I can pick a wavelength where only copper is going to absorb, but not the zinc. And then lastly, the reason why I'm also starting off by testing iron is because there are sometimes iron impurities in brass. And again, I don't want the iron to interfere with my percent copper measurement. So I'm going to test those three over the visible range so I can see what would be the best wavelength to figure out the percent of copper. Then what I'm going to do is I'm going to make a calibration curve of different copper 2+ solutions, so different concentrations, and then finally test my brass solution to figure out how much copper is in those brass pellets. So to start with, we're going to use our SpectroViz, and we do need to calibrate that. So I have here a cuvette filled with DI water, and I do want to use a Kim wipe, make sure there's no fingerprints. And I can skip the warm up because I have let it warm up for more than a minute and a half. So now I've zeroed out any absorbance that might be caused from the water because all of my solutions are aqueous. So let's start with our copper 2+ solution. And then we're going to use our iron 3+. And then finally our zinc 2+ solution. So what we see here is that the zinc 2+ does not absorb in the visible range, which makes sense because it is a colorless solution. So I actually wouldn't expect this to absorb in the visible range. We see that the absorbance of copper increases as the wavelength goes up, and the opposite is true for iron. So what I want to make sure to do is I want to pick a wavelength over here because the absorbance of both my iron and zinc are at a minimum, whereas the copper is absorbing highly. And so that way, if there is any iron impurity in my brass, I don't need to worry about that artificially increasing the absorbance of my samples. So looking at this, I'm probably going to pick a wavelength around 600 nanometers because again, that's where I'm seeing a minimum absorbance of my iron 3+ and my zinc 2+, but I am seeing a good absorbance for my copper solution. So now that I know what wavelength to set my SpectroVis to, now what I need to do is test the absorbance of different copper 2+ solutions that I've already made up. So we're going to have a 0.4 molar solution as well as a 0.2 molar, 0.1 molar, and 0.05 molar. And I made these solutions starting with the 0.4 molar and then measured out using my serological pipette how much of the stock solution versus how much of the water. So I already have those cuvettes filled and ready to go. So I'm going to go back to my Logger Pro. And again, I want to start with my copper 2+. And this is the 0.4 molar. Now, for this one, I don't want to do absorbance versus wavelength because I know what wavelength I want to take my measurements at. For making a calibration curve, I want to set this to absorbance versus concentration. So I'm going to configure this and select absorbance versus concentration. Now, I don't want the 798 wavelength. I want to go down to around, like I said, somewhere around 600 or so. and then hit OK. All right, so this is my 0.4 molar solution. And so you can see the absorbance down here. I'm gonna hit collect and then keep and type in that it is 0.4 molar. Next, I'm gonna test my 0.2 molar. Then 0.1. And then lastly, the 0.05 molar. And then we can take a look at these absorbances and see, even before we're done the lab, how good is our data? So since absorbance and concentration are directly proportional, when the concentration is cut in half, we should see that the absorbance is cut in half as well. And that is what we're seeing. So if the absorbance was 0.5 for the 0.4 molar, then I would expect an absorbance of 0.25 when it's 0.2 molar. Same thing as we go to 0.1 and then 0.05. So we can see that our data is matching up, and that's something we want to look at now rather than later when we're all done the lab. Because if I did see some sort of outlier here where the absorbance was too high or too low, that would be an indication that maybe I should remake one of the solutions again to make sure that the absorbance is reading where it should be. And then the last thing that we want to do is we want to test our brass solution to see how much copper is in this brass solution. Now, I can't hit keep up here because I don't know the concentration of the copper. But what I'm going to do is I'm going to record that absorbance value there. And then when I get the equation from the line, I can solve for the concentration of the copper in my brass solution. So I would simply record this number in my data table, but I'm not going to hit keep because I don't know the concentration. But now that I have my 4 known solutions, I can hit stop. And then we see that we have a pretty nice calibration curve. Our line is going through the origin, which is good because if my concentration were 0, I should expect the absorbance to be 0. My line is going through all of my data points. So I know that my calibration curve is a good one. And I'm going to use the equation here to solve for the percent copper in the brass. And so once I have that, now that will come out as molarity because that's how I entered in the concentration, but I can use the mass of the brass pellets to ultimately figure out the percent by mass of copper in those brass pellets.